roughly 26,700 light-years from where you are reading this, inside a cloud of gas near the center of our galaxy. Radio telescopes just caught the fingerprint of something that should not exist out there. Real sugar, the exact kind found inside a raspberry, sitting in a place with no star, no planet, and nothing alive for light-years in every direction. Scientists are calling it the first true sugar ever confirmed in the space between the stars, and its signal crossed 26,700 years of darkness just to reach a telescope dish in Spain. If sweetness like that can build itself with no star and no planet anywhere close, the raw ingredients for you may have been waiting in the dark long before Earth ever existed. If stories like this make the universe feel a little closer to home, all I ask is that you like this video and subscribe, so more of these can find their way to you. Get comfortable now and let your eyes rest. In 3, 2, 1, liftoff. Think back to the last time you tasted a truly ripe raspberry, the kind that comes apart the moment your fingers close around it, still warm from an afternoon spent sitting on the vine. Maybe it came from a farm stand you pulled over for on a summer drive, or a bowl someone set out at a family gathering, the kind of small, ordinary pleasure that never seems worth mentioning out loud. Perhaps your own grandmother stood over a hot stove some August afternoon, turning that same fruit into jam that would last the family clear through winter, sealed under wax in glass jars lined up along a pantry shelf. That specific sweetness, sharp and bright, with just enough tartness underneath to keep it interesting, comes partly from a particular sugar most people have never heard of and will likely never think about again after tonight. It is called erythrulose, and until just a few days ago, it was nothing more than a quiet footnote in the chemistry of fruit and an ingredient found in the kind of sunless tanning lotion that gives skin a golden color without a single minute spent under real sunlight. It shows up too in kiwi and in a whole quiet catalogue of other red and gold fruits most people have eaten 100 times without ever knowing there was a name for what made them taste the way they did. It has never been considered an important molecule. It has never made headlines. For as long as chemists have known its name, it has spent its entire existence doing small, forgettable work inside berries and bottles, the kind of molecule nobody outside a laboratory would ever think to look up. Then, a team of astronomers pointed 2 radio telescopes standing in the Spanish countryside toward a patch of sky near the center of our galaxy, and found that exact sugar drifting inside a cloud of gas and dust, so cold, so empty, and so far removed from anything resembling a kitchen table, that the discovery has quietly rewritten what scientists thought they understood about where the chemistry of life might actually begin. Not a cousin of that sugar, not a rough chemical sketch of it. Close, but not quite right. The very same molecule, carrying the very same 4-carbon frame found floating free in one of the most hostile stretches of the galaxy, a place with no fruit, no soil, no sunlight, and, as far as anyone can tell, nothing alive, for longer than the whole of human history has existed to go looking for it. This matters more than it might sound like it should, and it is worth sitting with for a moment before going any further into the story. Sugars like this one are not simple molecules, and they are not interchangeable with one another, the way the word sugar might suggest to someone who has only ever thought about the white granules kept in a kitchen canister. They belong to a small, particular family of compounds that biology leans on constantly, the same broad family that includes ribose, the sugar that forms part of the backbone of RNA, one of the 2 molecules every living thing on this planet depends on to store and carry forward its own instructions. Finding a true, complete sugar drifting loose in interstellar space, rather than locked safely inside a planet, a comet, or a piece of fruit, is the kind of discovery astronomers have been hoping for, and quietly doubting they would ever actually get to make. For decades, the molecule was not found floating in some empty stretch of open sky, the way a comet might be spotted crossing an otherwise dark patch of stars. It turned up inside what astronomers call a molecular cloud, one of the vast, cold nurseries of gas and dust that drift through the galaxy in the dark spaces between stars, largely unnoticed by anyone, without the right kind of instrument pointed in exactly the right direction. And this particular cloud sits in about as extreme a neighborhood as the Milky Way has to offer. Picture, for a moment, the kind of nebula you have likely seen glowing in photographs taken by space telescopes, one of those brilliant, colorful clouds that looks almost close enough to touch, backlit by the stars being born inside it, sculpted into pillars and arches by forces too large to really picture all at once. Molecular clouds are the quieter, colder cousins of those famous glowing nebulae, and most of them look nothing like the postcard images people usually associate with deep space. They do not blaze with color, because the light that would normally reveal their shape tends to get trapped or scattered by the sheer amount of dust packed inside them. In fact, if you have ever found yourself far from city lights on a truly dark, clear night, looking up at the pale band of the Milky Way stretched across the sky, you have likely already seen a molecular cloud without realizing it. Those dark, uneven rifts that seem to interrupt the brightness of the galaxy's band, the places where the glow looks thinner or briefly vanishes altogether, are not empty gaps at all. They are clouds like this one, dense enough with dust to blot out the light of everything behind them. To most telescopes that gather the kind of light human eyes can see, a molecular cloud like this one is close to invisible, a dark smudge against a brighter background, its true contents hidden until someone knows to look for it with the right kind of instrument entirely. What lies inside is anything but empty, though. Even in the coldest, quietest pocket of gas, molecules are forming, one slow chemical reaction at a time, drifting for what amounts to entire chapters of galactic history before anything happens to them at all. The Milky Way holds thousands of clouds like this one, scattered through its spiral arms and its crowded core, each one a slow-motion chemical laboratory of its own, each one destined, eventually, sometimes billions of years from now, to collapse under its own gravity and give birth to a new generation of stars, and presumably new planets circling them. Whatever chemistry has already assembled itself inside a cloud, by the time the collapse finally happens, does not simply vanish. It gets folded into whatever forms next, carried along like an inheritance nobody asked for and nobody can refuse. The particular cloud, where Erythrulos turned up, carries a name that sounds more like a coordinate than an actual place, because that is essentially what it is. Astronomers catalogue it as G plus 0.693 minus 0.027, a label built from its exact position on the sky rather than anything poetic, and it sits inside a much larger, far more famous complex of gas called Sagittarius B2, close to the very center of the Milky Way. This is not a quiet suburb of the galaxy. It sits deep inside the crowded, turbulent core, not far, in galactic terms, from the enormous black hole anchoring the middle of our galaxy, the one astronomers call Sagittarius A star. Stars are packed more tightly here than almost anywhere else in the Milky Way. Gravity pulls harder, radiation runs hotter, and the whole region hums with an intensity that the quiet, star-strewn sky above most American backyards gives no real hint of. On a clear summer night, away from porch lights and street lamps, Anyone can look toward the constellation Sagittarius, low along the southern horizon, and see the general direction of all of this without any equipment at all. The stars there simply look a little thicker, a little more crowded together than they do anywhere else in the sky. The way traffic on a highway grows denser the closer you get to a city center. What the naked eye reads as a modest brightening is, in truth, the visible edge of an entire galactic downtown, tens of thousands of light years deep, packed with more stars, more gas, and evidently more chemistry than anyone standing in a quiet backyard has any real way to imagine. And it is far, farther than most people ever try to picture in one sitting. The radio waves carrying the story of this discovery to Earth had to cross roughly 26,700 light-years of open galaxy to get here, a distance so large that the number itself starts to lose meaning the moment you say it out loud. Try it a different way instead. If a signal had left that cloud aimed at Earth back when the first cave paintings were being sketched onto stone walls in what is now France and Spain, long before the pyramids at Giza were ever stacked, long before anyone had thought to invent the wheel or the written word, that signal would only be arriving now, tonight, exactly in time for 2 radio dishes in Spain to catch it. Everything written in every history book you were ever assigned in school happened after that signal began its journey. Every language ever spoken, every war ever fought, every song anyone ever hummed while doing dishes at a kitchen sink happened somewhere inside that same stretch of crossing time. The entire rise and fall of every civilization anyone has ever studied fits comfortably inside the span of time this discovery has spent quietly crossing the galaxy to reach us. The scientist who found it is an astrochemist named Izaskun Jimenez Serra, who works at the Centro de Astrobiología, a research institute in Spain built specifically to study the chemistry that might eventually explain how life gets its start. For years, she and her research team have kept coming back to this same patch of galactic real estate, treating that one cloud less like a single subject and more like a favorite old fishing hole, the kind a person returns to again and again, because they already know it holds things nobody else has thought to look for. Over the years, that same cloud has quietly yielded discovery after discovery under her watch, a nitrogen-bearing molecule called hydroxylamine, believed to be an early stepping stone toward the chemistry that eventually builds amino acids, a close relative of ethanolamine, a compound found today in the fatty membranes wrapped around every living cell on Earth. Propanol, a simple alcohol, several nitrogen-rich molecules considered candidate precursors of the very backbone RNA, is built from. None of those earlier finds made international headlines the way this one has. Erythrulose is different, and everyone on her team seems to have understood immediately why. It is the first time anyone has pulled a true, complete sugar out of the dark rather than out of a laboratory, a meteorite, or a piece of fruit. If a molecule this specific could assemble itself in one cloud near the center of the galaxy, the same question immediately follows for every other cloud like it scattered throughout the Milky Way, and for the countless more scattered through every other galaxy within reach of a telescope. Nobody yet knows how common this kind of chemistry turns out to be. That is precisely the question Jimenez Serra's team has already turned its attention toward next. It is worth understanding, even briefly, what draws a scientist to spend years of a career pointed at one unglamorous patch of sky that most people will never hear the name of. The search Jimenez Serra and her colleagues are conducting is not really about sugar for its own sake. It is about a much older, much larger question, one that has occupied thoughtful people for as long as anyone has looked up at the night sky and wondered where all of this came from in the first place. Astrobiology, The field she works in exists specifically to chase questions like this one. Questions that take years or decades to answer, if they ever get answered fully at all. Every living thing on Earth is built out of a specific, fairly narrow set of chemical ingredients, sugars among them, and nobody has ever been entirely sure where those ingredients first came together. Did they assemble themselves here, in the shallow pools and warm chemistry of the young Earth, the way generations of textbooks have suggested? Or did some of the raw material arrive already partly built, carried here from somewhere else, delivered by comets and asteroids that had themselves been seeded, long before, by the same kind of slow, patient chemistry now being observed inside this cloud? It is a question serious enough, apparently, for one scientist to spend years of a working life chasing it through the coldest, quietest corners of the galaxy, patient enough to keep coming back to the same unglamorous cloud, long after any reasonable person might have moved on to something easier. That second possibility used to sound closer to folklore than to science. It sounds a great deal more plausible tonight than it did a week ago. None of this happened in isolation, and it helps to understand the much longer story this discovery quietly belongs to. Astronomers have been listening for molecules hidden inside clouds like this one since the 1960s, back when the very idea that interstellar space might contain any chemistry more complicated than loose atoms of hydrogen struck many scientists as unlikely. The first finds were almost disappointingly simple by comparison to what would come later: small molecules built from just a handful of atoms, discovered one at a time as radio telescopes slowly grew more sensitive and the catalogue of confirmed interstellar molecules grew, decade after decade, from a short list into a long one. Each new discovery pushed the boundary of what most scientists believed interstellar chemistry was capable of building. By the time Jimenez Serra and her generation of astrochemists came along, the question was no longer whether space could assemble anything complicated. It clearly could. The question that remained, the one this particular discovery finally answers, was whether it could assemble something as specific, as biologically meaningful as an actual sugar. What makes this particular cloud so useful to scientists searching for delicate molecules is, strangely enough, it's quiet. Most of the Milky Way's more famous star-forming regions, the kind that show up in glossy photographs under names like the Orion Nebula, are chaotic, violent places full of newborn stars blasting out radiation and shockwaves strong enough to tear fragile molecules apart before anyone gets a real chance to study them. This cloud, by contrast, is not actively building any stars of its own right now. It sits and waits, a patient reservoir of raw material, undisturbed enough that delicate, complicated molecules can survive inside it far longer than they would almost anywhere else nearby. That patience is precisely why it has become such a rich hunting ground. Astronomers have come to think of it as something close to a chemical archive, a place where the galaxy has been quietly writing down its own experiments for longer than anyone can say with real precision. One day, perhaps millions of years from now, gravity will finally win here too, and this same quiet stretch of gas will collapse inward and light up with newborn stars of its own, the same way countless clouds like it have done before across the long history of the galaxy. Until that day arrives, it remains exactly what makes it so valuable: undisturbed, unhurried, and open to careful listening. This single sugar did not arrive alone either. The same cloud is already known to host well over 100 other molecules, an entire hidden chemistry set drifting together through the same freezing dark, most of them far simpler than erythrulose, a few of them nearly as complicated. Untangling one signal from so crowded a mixture picking out the small number of individual radio frequencies that belong specifically to this one sugar and no other molecule sharing that same patch of sky, is part of what makes this discovery as demanding as it is remarkable. The cold inside is almost impossible to translate into anything a person standing in a kitchen in Ohio or Georgia has ever felt firsthand. The dust drifting through the cloud never climbs above roughly -423 degrees Fahrenheit, a depth of cold that would make the coldest winter night anyone reading this has ever endured feel, by comparison, like a mild spring afternoon. At those temperatures, molecules do not race around and collide the way they do in a warm kitchen or a simmering pot on a stove. They creep. They drift onto microscopic grains of dust, freezing into place the way frost gathers slowly across a window pane on a January night, and it is there, locked onto the surface of those grains, that some of the galaxy's strangest chemistry quietly gets to work. None of this happens quickly, and that slowness matters just as much as the cold does. A chemical reaction that would finish in an instant inside a lab on Earth might take years, decades, or far longer to complete inside a cloud like this one, where atoms and small molecules only occasionally drift close enough to react at all. Time, in other words, is doing some of the same work that heat usually does. Given long enough, even simple starting materials, a stray carbon atom here, a fragment of an oxygen-bearing molecule there, can slowly be stitched together into something as structurally particular as a sugar. Nobody built it. Nobody designed it. It assembled itself, one patient collision at a time, across a span of years that dwarfs the entire recorded history of human civilization. It is worth pausing here on the location itself, because scale is the only way any of this really lands. Our own solar system sits out in one of the Milky Way's quieter spiral arms, in a stretch of the galaxy where stars are spread thin and neighborhoods are calm, far removed from the crowded, turbulent core where this cloud makes its home. Nothing about where Erythrulos was found resembles home in any meaningful way, and that, more than anything else, is what makes its presence there so difficult to simply shrug off. And this is where the strangeness of the discovery really settles in, because everything about that location argues against finding anything like sugar there at all. Sugars, as far as anyone has ever observed them firsthand, belong to the world of biology. They are built by living things, or, at the very least, they show up in the debris left over from living things. Whether that is a raspberry ripening on a cane in early summer, or the ancient organic material locked inside a meteorite pulled out of a desert somewhere on Earth. Nothing about a cold, starless cloud near the violent core of the galaxy suggests biology of any kind. There is no soil there. There is no water pooling anywhere nearby, no sunlight warming anything, no green leaf turning ordinary air into anything sweet. And yet, the chemistry responsible for one of the most basic building blocks associated with life managed to put itself together anyway, using nothing but cold dust, patient time, and the same handful of common atoms, carbon, hydrogen, and oxygen, that show up nearly everywhere in the universe. It helps to think, for a moment, about what a sugar molecule actually needs in order to exist as a sugar at all, rather than as some looser, simpler cousin of one. It is not simply a jumble of the right atoms thrown together by chance. A true sugar has a specific architecture to it, a backbone with a particular arrangement of atoms and bonds that determines exactly what kind of sugar it becomes. Chemists sometimes describe the 4 carbon atoms at the heart of this particular sugar as a kind of skeleton key, small enough to be built almost anywhere, specific enough that only one exact arrangement counts as this molecule, rather than something close but different. Change the position of a single atom, and the result stops being erythrulose entirely and becomes something else, something with none of the same properties, none of the same relevance to the story of life. That precision is what makes its presence in open space so remarkable. The universe did not simply scatter carbon and oxygen and hydrogen atoms into a cloud and hope something useful came of it. Somewhere in that freezing dark, the correct arrangement happened, repeatedly and consistently, often enough for two radio dishes on the other side of the galaxy to notice the pattern and recognize it for what it was. Getting that arrangement right, out in the open chaos of interstellar space, without a cell, without an enzyme, without anything resembling the deliberate machinery a living organism would normally use to build a molecule, this specific is no small thing. It is closer to the difference between a pile of loose letters scattered across a table and those same letters somehow arranging themselves into a coherent word entirely on their own, with nobody there to sort them. There is something almost tender about that image, if you let yourself sit with it for a moment, instead of hurrying past it the way most headlines tend to. Somewhere out past the edge of anything resembling comfort, past the reach of any lit window or any familiar season, the raw material for sweetness has been quietly assembling itself in the dark, waiting for absolutely nothing, needing no audience, serving no purpose that anyone can yet identify. It did not know it would ever be found. It did not know it shared its shape with something growing on a bush in an American backyard. And somewhere on the other end of that same 26,700-year journey sits a kitchen counter, a mixing bowl, a hand reaching for a spoonful of sugar without a second thought, utterly unaware that the same molecule, in its simplest and most essential form, has just been found keeping company with a supermassive black hole. It simply existed, the way certain patterns in nature seem to exist whether or not anyone happens to be there to notice them. The way frost forms its own careful geometry on a window pane on a night when nobody happens to be looking out at it. Which raises the only question that actually matters at this point in the story. How does anyone find something like this in the first place? Nobody has ever traveled to that cloud. No spacecraft has ever passed anywhere near it, and none ever will in any lifetime that matters to us. Nobody has photographed it up close, held a sample of it, or studied it under a microscope the way a chemist might study a spoonful of sugar pulled down from a kitchen cabinet. The sugar itself gives off no visible light of its own. It cannot be seen, in any ordinary sense of that word, by any telescope built to gather the kind of light human eyes are able to perceive. And yet, Jimenez Serra and her team are confident enough in what they found to publish it, to put their names on it, to tell the world with real scientific certainty that this exact molecule exists in that exact place, 26,700 light years from where you are right now. That confidence had to come from somewhere. It came from two radio dishes standing quietly in the Spanish countryside, one of them 40 meters across, the other 30 meters wide, both of them built to listen rather than to look, tuned to catch the kind of faint, patient signal that a molecule like this one gives off as it tumbles slowly through the freezing dark. Picture them for a moment, if it helps to have somewhere to rest your attention before this part of the story continues later. One dish sits in the hills outside a small Spanish town called Yebes, not far from Guadalajara, its enormous white surface tipped toward the sky like an upturned face. The other sits near Granada, in the shadow of the Sierra Nevada mountains, part of a wider observatory built and shared by scientists from across Europe. Neither dish makes a sound a human ear could register. Neither one uses a single visible light to search the heavens. They simply sit, night after night, patiently turned toward one small, unremarkable patch of sky in the direction of the constellation Sagittarius, doing nothing that looks, from the outside, like discovery at all. What those two dishes managed to pull out of the static, and how a team of scientists turned that static into a confirmed discovery precise enough to publish to the entire scientific world, is a story worth sitting with in its own right. It involves matching an impossibly faint signal from the middle of the galaxy against a fingerprint measured carefully, patiently, in a laboratory here on Earth, one that had to be built almost from scratch because nobody had ever needed to measure the radio signature of this particular sugar before. What happened inside that laboratory, and how a syrupy, sticky molecule that refuses to cooperate even under controlled conditions here on Earth became the key to confirming something 26,700 light-years away, is where the real detective work of this discovery begins. For now, it is enough to know that the signal made it. After 26,700 years of crossing empty space, after drifting silently past countless other stars and other clouds that never happened to be listening, it finally found two dishes in the Spanish countryside that were. A signal alone proves nothing. That is the uncomfortable truth sitting underneath every radio astronomy discovery, and it is exactly the wall Jimenez Serra and her team ran into the moment their two dishes in Spain pulled something unusual out of the static. Radio telescopes do not see molecules the way a photograph shows a face. They record a long, tangled ribbon of frequencies, thousands of overlapping signals bleeding into one another, arriving from every corner of a cloud that already hosts well over 100 other molecules drifting through the same freezing dark. Somewhere buried inside that ribbon sat the frequencies belonging to a sugar nobody had ever confirmed existed anywhere beyond a kitchen or a laboratory. Finding it meant knowing, ahead of time, exactly what to look for. Every molecule in the universe has a shape, and shape is not a small detail. It determines how a molecule spins, how it bends, how its atoms rock back and forth against each other in the near vacuum of space. Each of those tiny motions releases or absorbs energy at a frequency dictated entirely by the molecule's structure. The way a specific length of guitar string will only ever ring out at one particular note, no matter how many other strings happen to be vibrating around it. Line up enough of those frequencies together, and you get something as unique and unmistakable as a fingerprint pressed into ink, a signature no other molecule in the universe happens to share. Astronomers call this rotational spectroscopy, and it has become the primary tool for identifying what actually exists in the space between stars, since nobody can travel there to check directly. When researchers finally sit down to examine data like this, what they are looking at is not a photograph or anything resembling one. It is closer to a long, jagged mountain range drawn on a chart, thousands of individual peaks and valleys stretched across a page, each peak marking a frequency where something out in that cloud released a little more energy than the quiet background around it. Most of those peaks, on their own, mean almost nothing. Only when a researcher lines up a whole cluster of them against a known fingerprint, checking whether they fall exactly where a specific molecule predicts they should, does any single peak start to mean anything at all. The two telescopes involved cover an enormous stretch of that radio spectrum between them, scanning across more than 91 gigahertz of frequency space in total, spread across 3 separate atmospheric windows that radio waves can pass through cleanly on their way down from space. Think of it the way you might think of slowly turning the dial on an old AM radio except instead of covering the small range of frequencies used for broadcasting music and talk shows, this search swept across a band of radio frequencies far wider than anything a household radio was ever built to reach, patiently checking each one for a signal that might belong to erythrulose. That breadth matters enormously. A narrow search might miss a molecule's fingerprint entirely simply by looking in the wrong slice of the dial. A survey this wide gave the team a real chance of catching erythrulose's signature wherever it happened to fall, rather than hoping to get lucky with a narrower search aimed at a single guess. But a fingerprint is only useful if you already have another one to compare it against. This is where the discovery nearly stalled before it properly began. Nobody had ever measured the radio fingerprint of erythrulose before, not once in the entire history of chemistry. The molecule had spent its whole existence quietly doing its work inside fruit and lotion bottles, never once needing to reveal its rotational signature to anyone, because nobody had ever needed to look for it, drifting through open space. Before the team could search the sky with any real confidence, they first had to build the very reference they were missing, here on Earth, in a laboratory, molecule by molecule. That task fell partly to researchers at the University of the Basque Country, working in a laboratory thousands of miles from either radio dish, tasked with measuring erythrulose's radio fingerprint under carefully controlled conditions. It sounds, on paper, like a straightforward job. Take a small sample of the sugar, heat it gently until it turns to gas, and record exactly which frequencies it absorbs and releases as it spins. In practice, it turned into one of the more stubborn technical puzzles behind this entire discovery, because sugars, as anyone who has ever scorched a pan of caramel on a stovetop already knows in their bones, do not behave politely when heated. Erythrulose exists at room temperature as a syrupy, sticky liquid, closer in texture to warm honey than to anything resembling table sugar's familiar white crystals. Heated directly, the way you might heat any ordinary substance to coax it into a gas, and it does not politely evaporate into a clean, measurable vapor. It breaks down instead, its careful four-carbon architecture falling apart into simpler fragments before it ever has the chance to reveal its true rotational fingerprint. A destroyed molecule tells you nothing. The chemists needed erythrulose to arrive in the gas phase fully intact, its structure undisturbed, and ordinary heating simply would not get them there. Their solution was almost startlingly simple, the kind of fix that sounds more like a grandmother's trick than a piece of advanced laboratory technique. The researchers mixed the syrupy sugar with ordinary talc powder before heating it. The talc acted like a kind of scaffolding, spreading the sugar thin across an enormous hidden surface area and helping individual molecules break free into the gas phase gently, one at a time, before the heat had any real chance to tear them apart. It is the same basic principle behind spreading batter thin across a griddle instead of dropping it into the pan as one thick lump, giving the heat less material to overwhelm at any single point. With that problem solved, the erythrulose finally cooperated, rising into the gas phase intact and ready to be measured. Once erythrulose existed as an intact gas, spectroscopists could finally do the careful, patient work of recording its true fingerprint, sweeping across a wide range of frequencies and noting every single one where the gas absorbed or released energy as it tumbled and spun. That fingerprint, once measured, became the master reference the entire discovery depended on. Without it, the signal sitting inside the radio data collected in Spain would have remained exactly what it had always been, an unidentified whisper gathered from the sky but never understood. None of this happened inside a single building, or even a single country. The radio observations came from Spain. The laboratory measurements came from the University of the Basque Country, also in Spain. But the modeling and analysis that tied every piece together drew on an international team of collaborators. The kind of quietly cooperative effort that rarely makes it into a headline, but sits behind nearly every major discovery in modern astrochemistry. Confirming a single molecule this precisely is not the work of one scientist working alone in a room. It takes telescopes built by one group, spectroscopy performed by another, and careful cross-checking by still others, all of it converging on the same 12 numbers before anyone felt confident enough to publish. Armed with that laboratory fingerprint, the team returned to the mountain of radio data collected by the Yebes and IRAM telescopes and began the painstaking work of searching for a match. This is where the crowded nature of that particular cloud became both a blessing and a genuine obstacle. A cloud hosting well over 100 other molecules produces a radio spectrum so densely packed that individual signals constantly overlap, blur together, and disguise themselves as something else entirely. Finding erythrulose's fingerprint inside that noise meant checking, frequency by frequency, whether each line predicted by the laboratory measurement actually showed up in the data, and whether it showed up cleanly enough to trust. In total, 12 separate frequencies lined up with the laboratory prediction closely enough to count as a genuine match. 12 individual signals belonging unmistakably to erythrulose, and nothing else drifting through that same cloud. Of those 12, 6 stood apart from the surrounding noise almost entirely, clean and unambiguous, largely free of interference from any of the cloud's many other residents. The remaining 6 were harder to isolate completely, partially tangled with signals from neighboring molecules, but consistent enough with the pattern to reinforce rather than undermine the case. A scientist has to be honest about which of the 12 belong in that first, cleaner group and which belong in the second, and the published research does exactly that, drawing a clear line between the lines that stand alone and the ones that needed a more careful eye to untangle from their neighbors. Finding one matching frequency might be coincidence. Finding 12 in the exact pattern the laboratory predicted is not. Part of why this particular cloud kept yielding matches clean enough to trust comes down to something almost paradoxical about its physical conditions. Despite its cold, its gas is thin enough that molecules rarely collide with one another, and that matters more than it might sound like it should. In a denser environment, constant collisions blur a molecule's radio signal, smearing what would otherwise be a sharp, narrow spike into something wider and messier, harder to distinguish from its neighbors. In this cloud's comparatively thin gas, each spectral line stays narrow and well-defined, exactly the kind of clean signal a matching process like this one depends on. Confidence like that does not come cheaply in this field, and it should not. Astronomy has a long history of announcements that seemed solid at first and quietly fell apart under closer scrutiny, a signal that looked promising turning out to be interference from Earth's own atmosphere, or a coincidental overlap between two entirely unrelated molecules that happen to share a frequency by chance. Scientists who study the interstellar medium have grown deliberately cautious as a result, insisting on multiple independent lines of evidence before anyone is willing to put their name on a claim this significant. A single matching frequency invites skepticism. A cluster of 12, checked individually against contamination from every other known molecule in that same crowded cloud, is what finally clears the bar that peer review demands before a result like this reaches a journal as respected as the one this discovery was published in. Even after publication, the story is not entirely finished. Other research groups, working with their own telescopes and their own laboratory equipment, will likely spend the coming months attempting to independently confirm the same 12 frequencies in the same cloud, the way any significant scientific claim eventually gets tested by hands other than the ones that first made it. Independent confirmation, more than any single announcement, is what ultimately cements a discovery like this one into settled scientific fact, rather than a single team's promising result. For every molecule that ends up confirmed and published, astrochemists sift through far more candidates that never make it that far. A frequency that looks promising on a Tuesday afternoon might turn out, after weeks of careful cross-checking, to belong to some far more mundane molecule already well known to science, or to nothing at all beyond ordinary noise in the data. This kind of research rewards patience more than almost anything else, the willingness to spend months verifying a result before ever announcing it, and the discipline to abandon a promising lead the moment the evidence stops holding up. Jimenez Serra's team has spent years building exactly that kind of patience into their approach to this one particular cloud, which may explain why, when a genuine discovery like this one finally does arrive, the confidence behind it runs so deep. 12 confirmed frequencies settled the question of whether erythrulose exists inside that cloud. They did nothing on their own to settle a second, more subtle question that turned out to matter just as much: whether erythrulose actually deserves to be called the first true sugar ever found in interstellar space, a title that, as it happens, had technically been claimed once before. Back in the year 2000, a team of astronomers led by John Hollis detected a much smaller molecule called glycolaldehyde drifting through that same general neighborhood near the galactic center in the wider Sagittarius B, too complex that this newer cloud belongs to. Glycolaldehyde carries only 2 carbon atoms in its frame, half of what erythrulose carries, and the paper announcing its discovery was even titled, quite directly, Interstellar Glycolaldehyde, the First Sugar. For more than 2 decades, that title stood largely unchallenged. It was, and still is, considered a landmark discovery, the very find that first convinced astrochemists it was worth searching for sugar-related molecules in space at all. 26 years is a long time to keep searching for something without knowing whether it exists at all. That is roughly how long separates glycolaldehyde's discovery from this one. Over 2.5 decades of increasingly sensitive telescopes, increasingly patient scientists, and increasingly refined laboratory techniques, all aimed at climbing one single rung higher on a ladder that most researchers assumed, for long stretches of that time, might simply be too fragile a stretch of chemistry for the universe to bother completing. But chemistry, like most careful fields, tends to sharpen its own definitions over time. A true sugar, in the strict sense chemists use today, needs a specific kind of backbone, at least 3 carbon atoms arranged with a particular pattern of bonds and oxygen atoms that defines an entire family of molecule called monosaccharides. Glycolaldehyde, with only 2 carbons, falls one short of that threshold. It is a genuine, important, sugar-related molecule and a real and significant piece of prebiotic chemistry in its own right, but by the specific structural definition biochemists rely on. It functions as a building block on the way toward a sugar rather than as a complete sugar itself. Erythrulose, with its 4-carbon frame and its particular arrangement of bonds, clears that threshold cleanly. It belongs to a family chemists call ketoses, and within that family, it happens to be the smallest possible member, the very first rung on the ladder where the word sugar, used in its full and proper sense, actually applies. This is not the first time this same cloud, or scientists working closely with Jimenez Serra, has been searched for a piece of this exact puzzle. Back in 2020, her team specifically went looking for glyceraldehyde, the 3-carbon sugar that would have sat neatly between glycolaldehyde and erythrulose on that same ladder, the logical next step upward. They did not find it. That absence, rather than weakening the story, sharpens it considerably. The chemistry of this particular cloud appears to have skipped directly past the middle rung and produced, in meaningful quantities, the 4-carbon sugar instead, a detail that raises more questions than it answers about exactly how this molecule assembled itself in the first place. The same survey that finally turned up erythrulose also went looking specifically for 2 other 3-carbon sugars, close chemical relatives called glyceraldehyde and dihydroxyacetone, the kind of molecules a chemist might expect to find, sitting comfortably in between glycolaldehyde's 2 carbons and erythrulose's 4. Neither one turned up, not even in trace amounts, despite a survey sensitive enough to have caught them if they were there at all. Erythrulose, meanwhile, showed up in quantities at least 8 times greater than the upper limit those undetected 3-carbon sugars could possibly have reached without being noticed. It is a strange kind of imbalance. Ordinarily, chemists studying molecular clouds expect complexity to build gradually, smaller molecules outnumbering larger ones, each step up the ladder rarer than the step before it. 2 carbons should be common. 3 carbons should be less common. 4 carbons should be rarer still. Instead, this particular cloud appears to have produced more of the rarer 4-carbon sugar than either of the 3-carbon sugars that, by most expectations, should have been sitting there in greater abundance. Nobody yet has a settled explanation for why. One possibility under consideration is that erythrulose forms through a chemical pathway that simply bypasses the 3-carbon stage entirely, built directly from smaller 2-carbon fragments locked onto the icy surface of dust grains, rather than climbing the ladder rung by rung, the way chemists originally assumed complexity had to build. If that turns out to be correct, it would mean the galaxy has more than one route to a sugar, and the shortest route is not necessarily the one anyone would have guessed. There is another way to read that imbalance too, one that has less to do with chemistry and more to do with time. If 4-carbon sugars accumulate while 3-carbon ones do not, perhaps the chemistry inside this particular cloud has simply had unusually long to work, favoring whichever reaction pathway happens to run fastest over the huge stretches of time available. Even if that pathway skips past intermediate steps, a laboratory experiment on Earth, working on a human timescale of hours or days, would never have the patience to observe. A cloud like this one measures its own chemistry not in afternoons, but in something closer to geological time, and what looks like an unusual shortcut from the outside may simply be the ordinary outcome of running the same slow reaction for far, far longer than anyone on Earth has ever had the patience or the years to wait. There is a second, entirely separate property of this molecule that makes its discovery even more remarkable, one that has nothing to do with how many carbon atoms it carries and everything to do with its shape. Hold your 2 hands up in front of you, palms facing each other. They are mirror images, identical in every measurable way, the same number of fingers arranged in the same pattern, yet no amount of turning or rotating will ever let your left hand fit perfectly into a right-handed glove. That property, the existence of 2 versions of the same object that are mirror images of each other but can never be perfectly superimposed, is called chirality, and it is one of the deepest, strangest features written into the chemistry of life itself. Chemists have understood that some molecules carry this kind of handedness for well over a century and a half now. The French chemist Louis Pasteur first noticed it back in 1848, sorting through crystals of a substance called tartaric acid under a simple microscope, using nothing more sophisticated than a pair of tweezers to separate two kinds of crystal that were chemically identical in every measurable way except their shape, mirror images of one another, exactly like a left hand and a right hand. It was one of the earliest hints that the physical shape of a molecule, not just its ingredients, could matter enormously, an idea that would eventually become central to understanding how life itself is put together. Nearly every molecule essential to biology comes in this kind of mirror image pair, and strangely, life on Earth almost never uses both versions equally. The amino acids that build every protein in your body are, with only rare exceptions, exclusively left-handed. The sugars that build the backbone of your DNA and RNA are just as consistently, exclusively right-handed. Nobody fully understands why life settled so decisively on one hand over the other, out of two versions that behave almost identically in a laboratory. It remains one of the genuinely open questions in the story of how life began, and it is a question this molecule speaks to directly, because erythrulose itself is chiral. This is only the second time in the entire history of radio astronomy that a chiral molecule of any kind has been confirmed drifting through interstellar space. The first came nearly a decade earlier, back in 2016, when a research team using the Green Bank telescope in West Virginia, along with the Parkes radio telescope in Australia, detected a molecule called propylene oxide inside that very same broader Sagittarius B2 complex. That earlier discovery made headlines of its own at the time, not because propylene oxide itself carries any special biological significance, but because it proved, for the first time, that chirality, this deep asymmetry sitting at the foundation of biology, is something the universe is capable of producing on its own, out in open space, long before anything alive exists to make use of it. Propylene oxide, for all its historical importance as a first, is not a molecule biology has any particular use for. It shows up on Earth mostly in industrial chemistry, a building block for certain plastics and solvents, useful to a factory but irrelevant to a living cell. Erythrulose is different. It sits inside the same broad family of molecules that DNA and RNA depend on directly. Finding chirality this time inside an actual sugar, rather than inside a molecule with no real biological role, draws the connection between cosmic chemistry and the chemistry of life a good deal tighter than the first discovery ever could. To put that rarity in perspective, astronomers have now confirmed several hundred distinct molecules drifting somewhere in interstellar space, everything from simple two-atom fragments to sprawling ring-shaped structures built from dozens of atoms. Out of that entire catalogue, built up over more than 6 decades of careful listening, only 2 have ever been confirmed to carry this particular kind of handedness. Chirality, it turns out, is not something the universe hands out casually. Finding a second chiral molecule now, a full 10 years later, and finding it to be an actual sugar rather than an industrial compound, adds real weight to a question that has quietly occupied astrochemists ever since that first discovery. If space itself can produce molecules with a preferred handedness, even occasionally, could that early asymmetry have been carried along into the raw material that eventually built the first living things on Earth, rather than that asymmetry emerging later, here, through some process unique to our own planet? One leading hypothesis, still far from settled, proposes that the intense radiation inside active star-forming regions can become polarized in a way that destroys slightly more of one chiral version of a molecule than the other, tipping the balance ever so slightly before that material ever gets anywhere near a planet. It remains a hypothesis rather than a proven mechanism, but every new chiral molecule found in a place like this gives researchers one more data point to test it against. There is a broader hunt underway that this discovery quietly feeds into as well. Scientists searching for signs of life on planets orbiting distant stars have long wrestled with a difficult problem. What, exactly, should count as convincing evidence of biology, as opposed to ordinary chemistry that happens to look interesting? A single sugar molecule or a single amino acid proves very little on its own, because chemistry alone can produce plenty of molecules that merely resemble the building blocks of life without actually indicating anything is alive nearby. But a consistent excess of one chiral form over its mirror image, what chemists call an enantiomeric excess, is much harder to explain through ordinary chemistry alone. It is the kind of signature many researchers consider a genuinely promising clue, one that future telescopes and future missions may eventually be built specifically to search for in the atmospheres of planets circling other stars. Erythrulose itself is far too faint and far too distant to serve as that kind of direct evidence. But every confirmed chiral molecule found drifting through interstellar space adds one more thread to the argument that this deep asymmetry is not a fluke unique to Earth, and that argument matters enormously for anyone hoping to eventually recognize life somewhere else, if it exists at all. Put all of it together, and the picture that emerges is stranger and more specific than the opening discovery alone suggested. This is not simply a sugar that happens to exist somewhere cold and far away. It is a true, complete, 4-carbon monosaccharide, confirmed through 12 independent spectral lines matched against a laboratory reference that had to be built from scratch, present in quantities that outpace its simpler chemical relatives for reasons nobody yet fully understands, and carrying the same fundamental handedness that biology itself depends on. Every piece of that description points toward the same unsettling question. None of the 12 confirmed lines, none of the careful laboratory work, none of the 8 times abundance measurement, and none of the second ever chiral molecule designation changes one simple, stubborn fact. Everything just described happened 26,700 light-years away, in a place no human being, no spacecraft, and no future mission currently on any drawing board will ever visit directly. If a molecule this specific, this fragile, and this biologically relevant can assemble itself inside a cloud sitting 26,700 light-years from the nearest kitchen table, the question stops being whether the chemistry of life can get a head start out in the dark. The evidence for that much is already sitting confirmed in a peer-reviewed journal. The question that remains, the one this discovery cannot answer on its own, is how anything built that far from anywhere ever crosses the enormous gulf between an interstellar cloud and an actual planet. A molecular cloud like this one is not going anywhere near Earth, not now, not in any time frame a person could reasonably picture. So how, if the raw material for sweetness really has been quietly assembling itself in places like this since long before our solar system even existed, does any of it ever find its way somewhere that matters? A molecular cloud does not sit still forever. Given enough time, usually many millions of years, gravity always wins. Dense pockets within a cloud like this one eventually collapse under their own weight, drawing surrounding gas and dust inward, spinning faster as they shrink. The way a skater's spin quickens when her arms pull in close to her body. At the center of that collapse, pressure and temperature climb high enough to ignite nuclear fusion, and a new star switches on. That whole process, From a quiet, cold pocket of gas first beginning to contract to a fully formed star switching on at its center, typically unfolds over something on the order of 100,000 years. A blink of an eye by the standards of a galaxy that has existed for more than 10 billion years, but a span of time that dwarfs every single human civilization that has ever risen and fallen. Around that newborn star, the leftover material, everything that did not fall directly into the growing flame, flattens into a wide, spinning disk, the same basic shape every solar system in the universe seems to share, including our own. This is the part of the story where a crucial distinction has to be drawn clearly, because it would be easy and wrong to let the excitement of this discovery blur an important line. The cloud where Erythrulose was found is not, and never was, the cloud that formed our own solar system. That collapse happened 4.5 billion years ago, in a different pocket of the galaxy entirely, long before this particular molecular cloud, or the black hole it now drifts near, existed in anything like their current form. What this discovery offers is not a family photograph of our own origins. It is closer to a photograph of a distant cousin, living in a different city, whose kitchen happens to contain the exact same recipe box. Astronomers cannot point to the exact cloud that gave birth to our sun. That particular cloud dispersed long ago, its material scattered across the galaxy over billions of years of orbital motion, its identity as a single coherent structure lost to time. In the same way, a specific wave becomes impossible to trace once it has long since rejoined the ocean. What they can say with reasonable confidence is that our sun almost certainly did not form in isolation. Stars, like the sun, typically form in clusters, dozens or hundreds of stars, condensing out of the same collapsing cloud at roughly the same time, siblings born from the same reservoir of gas and dust before eventually drifting apart, scattered across the galaxy by the ordinary gravitational tug of everything else moving around them. Astronomers have tried, in fact, to track down some of the sun's long-lost siblings using exactly the same principle behind identifying Erythrulose in the first place, a fingerprint just built from a different kind of evidence. Stars that form together from the same cloud tend to share a distinctive chemical signature in their light, trace amounts of specific elements locked into their outer layers in matching proportions, evidence of having condensed from the exact same reservoir of material. A handful of candidate stars scattered across the sky have chemical signatures close enough to the sun's own to raise real suspicion that they might be genuine siblings, born from the same collapsing cloud roughly 4.5 billion years ago. None has been confirmed beyond doubt. The stars have simply drifted too far apart, and too much time has passed for certainty to come easily. What it tells us, with real confidence, is something different but still remarkable: that the particular kind of chemistry needed to build a molecule like Erythrulose is not some impossibly rare fluke, dependent on conditions found in one single, irreplaceable place. It is the kind of chemistry that molecular clouds, as a general category, seem capable of producing, given enough cold, enough dust, and enough patient time. And if it can happen there, in a cloud we can actually observe today, there is no obvious reason it could not have happened in roughly the same way, inside whatever cloud eventually collapsed to form the sun, the Earth, and everything orbiting between them. To understand how a molecule this specific could assemble itself inside any molecular cloud, picture the surface of one of those microscopic dust grains scattered through the freezing dark, coated in a thin crust of ice, built from simple, common molecules: water, carbon monoxide, and a small, humble molecule called formaldehyde, the same substance long used in far higher concentrations to preserve biological specimens in jars back on Earth. Formaldehyde itself is a startlingly common molecule out in interstellar space, one of the simplest carbon-bearing molecules known, found scattered through countless clouds across the galaxy. On the icy surface of a dust grain, individual formaldehyde molecules occasionally drift close enough to react with one another, especially when a passing shock wave or a burst of radiation supplies just enough extra energy to nudge the reaction forward. That extra nudge of energy does not come from nowhere. Molecular clouds are far from perfectly still environments, despite their apparent calm. Distant supernova explosions send shockwaves rippling through the galaxy over thousands of years, compressing pockets of gas and dust as they pass. Cosmic rays, high-energy particles racing through space at nearly the speed of light, constantly bombard these clouds as well, occasionally striking a molecule with enough force to break a chemical bond or knock loose an atom ready to bond with something new. Neither event happens often to any single molecule. Across a cloud containing enough raw material to build hundreds of thousands of stars, and across enough time, rare events add up into a steady, ongoing trickle of chemistry. The broader complex this cloud sits within, the same Sagittarius B2 region already described, contains a mass of gas and dust equivalent to roughly 3 million suns, spread across a volume of space large enough that light itself would need years to cross from one edge to the other. Scale on that order changes the arithmetic of probability entirely. What looks impossibly unlikely for one grain, one molecule, one single collision becomes something closer to a statistical certainty once multiplied across a reservoir of raw material that size, patiently allowed to run for the better part of 1 million years. Two formaldehyde molecules combining can produce glycolaldehyde, the same two-carbon molecule first detected back in the year 2000. From there, chemists suspect additional carbon-bearing fragments can attach themselves one at a time, extending that same basic backbone further. 3 carbons, then 4, each addition a small, individually unremarkable event, happening across a span of time that makes any laboratory clock feel almost meaningless. Chemists sometimes describe the surface of these icy grains as a kind of workbench, the only stable, solid platform in an otherwise near-empty void, where molecules can actually sit still long enough for a reaction to occur. Out in the open gas of the cloud, molecules are moving too fast and colliding too rarely for anything complicated to assemble. On the workbench of a grain's icy surface, they can linger, bump against their neighbors repeatedly, and, every so often, over the course of many thousands of years, snap together into something larger than either one alone. It is patient, unglamorous, unsupervised work carried out without a single conscious hand ever guiding it, and it is the leading explanation chemists currently have for how a molecule as specific as erythrulose could exist at all in a place with no laboratory, no cell, and no chemist standing by to help it along. Nobody can watch this chemistry happen in real time, of course. The timescales involved stretch so far beyond a human lifespan, let alone a laboratory experiment, that scientists instead have to infer the process from its results, the way a detective reconstructs an entire evening from the scattered evidence left behind the next morning. A single collision between two molecules on the surface of a dust grain might be a genuinely rare event, occurring perhaps once every few thousand years for any specific grain. But a molecular cloud does not contain one grain. It contains something on the order of quadrillions upon quadrillions of them, each one running its own version of the same slow experiment simultaneously across a span of millions of years. This proposed pathway remains a leading hypothesis rather than a fully confirmed mechanism, and the research team behind this discovery was careful to test it as best they could. One reasonable prediction, if this general picture is correct, involves a molecule called glycerol, a simple 3-carbon compound that some models suggest could serve as an intermediate step, or at least a closely related byproduct, somewhere along the same general chemical pathway that builds erythrulose. If that prediction held, glycerol should have shown up in the same survey, drifting through the same cloud in measurable quantities. It did not. The team searched specifically for glycerol's own radio fingerprint within the same data and came up empty, the same way earlier searches for the 3-carbon sugars glyceraldehyde and dihydroxyacetone came up empty. This is exactly the kind of honest, unglamorous result that rarely makes it into a headline, a hypothesis tested carefully and not confirmed. But it matters enormously for understanding how much of this story is settled and how much remains genuinely open. Erythrulose's existence inside that cloud is not in question. Precisely how it got there, atom by atom, step by step, still is. Whatever cloud actually did collapse to build our solar system almost certainly carried its own version of this same slow chemistry, ice-coated grains scattered throughout it, each one a tiny workbench of its own, each one capable of building up molecules in exactly the pattern being observed now in this unrelated cloud. When that collapse began, all of that pre-built chemistry did not simply vanish. It got carried along, the way a river gathers sediment as it flows and eventually deposits that sediment somewhere far downstream, reshaped by the journey but not erased by it. As the collapsing cloud flattened into the spinning disk that would eventually become our solar system, the dust grains inside it, chemistry and all, became part of the raw material from which everything else was built. Those dust grains did not stay scattered as fine powder forever either. Within that spinning disk, grains collided and stuck together, slowly building upward in scale, from specks of dust to pebbles, from pebbles to boulders, from boulders to the planetesimals that would eventually become comets, asteroids, and, in time, the rocky planets themselves. Each step in that upward climb had the chance to lock a little more of the original ice grain chemistry safely inside it, sealed away from the harsh radiation of the newborn sun, preserved in cold storage inside bodies that, in some cases, have remained largely unchanged for 4.5 billion years. This is not simply a plausible story stitched together after the fact. Comets and asteroids that have survived largely unchanged since the solar system's earliest days occasionally cross paths with Earth, and when fragments of them survive the fall through the atmosphere, they land as meteorites, physical time capsules carrying a chemical record of conditions that existed before the Earth itself had finished forming. And when scientists have opened those time capsules and looked closely, they have, in fact, found sugars waiting inside. In 2019, a research team led by Yoshihiro Furukawa, working with NASA and Tohoku University in Japan, examined 2 carbon-rich meteorites, one called Murchison, which fell across the Australian countryside back in 1969, and another called Northwest Africa 801, recovered from the Sahara. Using careful extraction techniques, the team searched for a family of 5 carbon sugars, including ribose itself, the very sugar that forms part of the backbone of RNA. Meteorite hunters and planetary scientists add new specimens to the world's collections regularly, some falling freshly from the sky and recovered within days, others discovered decades after landing, sitting undisturbed in a desert or an ice field, until someone finally noticed them. Each new carbon-rich meteorite that turns up represents another opportunity to test whether this same pattern of sugars, amino acids, and other prebiotic chemistry holds true generally, or whether Murchison and Northwest Africa 801 was simply an unusually fortunate pair of finds. They found it. Ribose turned up in both meteorites, alongside 3 closely related sugars at concentrations measured in parts per billion, faint but genuinely, unmistakably present, roughly comparable to finding a single grain of salt dissolved somewhere within an entire swimming pool of water. A third meteorite, called Northwest Africa 7020, underwent the exact same testing and turned up nothing, no detectable sugars at all, a result that on its own might have raised doubts about the whole finding. Instead, it strengthened the case considerably. That particular meteorite had experienced far more exposure to liquid water sometime during its long history than either Murchison or Northwest Africa 801, and water is known to break sugars down over time. Finding sugars precisely where the geological history predicted they should have survived, and finding none precisely where that same history predicted they would have been destroyed, is exactly the kind of internally consistent pattern that separates a genuine scientific result from a lucky coincidence. Skeptics raised an obvious question immediately. Could those sugars simply be contamination? Terrestrial sugar that had somehow worked its way into the meteorite sometime after it landed on Earth. Furukawa's team anticipated exactly that challenge and checked for it directly, examining the specific carbon isotopes locked inside the sugar molecules themselves. Carbon that formed here on Earth carries a slightly different isotopic signature than carbon that formed in space, a kind of chemical birth certificate that survives even after everything else about a molecule has been transformed. The sugars pulled from Murchison and Northwest Africa 801 carried the signature of space, not of Earth. They were not contamination. They were exactly what they appeared to be, genuine extraterrestrial sugar, older than the planet it eventually landed on. Sugars were not the only building blocks of life. This same kind of testing has identified inside carbon-rich meteorites over the years. Amino acids, the building blocks proteins are made from, and nucleobases, components of the genetic code itself, have both turned up in similar material as well, suggesting that when a body like this one falls to Earth, it does not necessarily arrive carrying just one isolated ingredient, but something closer to a partial, jumbled pantry of the chemistry life eventually came to depend on. Meteorites are not the only physical evidence supporting this general picture. In 2016, a spacecraft got close enough to an actual comet to measure its chemistry directly, without waiting for a fragment to fall to Earth first. The European Space Agency's Rosetta mission spent months orbiting a comet named 67P Churyumov-Gerasimenko, using an instrument called Rosina to sample the thin cloud of gas surrounding the comet's icy core as sunlight slowly warmed it. Inside that gas, scientists found glycine, the simplest of the 20 amino acids that build every protein in every living thing on Earth, along with phosphorus, an element essential to both DNA and RNA. The Rosetta mission itself was a decade-long undertaking, launched in 2004, and finally arriving at its target comet a full 10 years later. After a journey that looped past Earth and Mars multiple times to build up enough speed for the rendezvous, Rosetta carried with it a small lander named Philae, which touched down on the comet's surface later that same arrival year, the first spacecraft in history to land gently on a comet rather than simply crashing into one or flying past. The chemistry data that eventually revealed glycine came primarily from the orbiter itself, patiently circling the comet for roughly 2 years, close enough to sample its thin atmosphere directly as the comet swung nearer to the sun and began to warm. This was a genuinely significant moment in the search for life's raw ingredients, because it meant scientists were no longer relying entirely on fragments that had already survived a fiery plunge through Earth's atmosphere and years of exposure sitting in a desert or an ice field somewhere. They were measuring a comet's actual chemistry directly at the source, largely undisturbed since the solar system's earliest days. What made this particular detection especially relevant to the story of erythrulose was not the amino acid itself, but where scientists believe it came from. The glycine detected around that comet appears to have been released from the icy grains making up the comet's core, warming and evaporating as sunlight reached them, the same basic kind of icy grain this entire story has centered on from the start. A comet, in other words, appears to function as a kind of cold storage vault, carrying chemistry built long ago on grain surfaces and releasing it gradually, molecule by molecule, whenever conditions finally allow. Glycine is not a sugar, and this particular comet mission was never looking for erythrulose specifically, but the underlying mechanism on display, prebiotic chemistry assembled on icy grains and later released intact from a comet as it approaches a warming star, is exactly the mechanism this entire chain of evidence depends on. Different molecule, same delivery system. Even a successful delivery does not guarantee anything happens next. A comet or asteroid carrying this kind of chemistry might just as easily strike a gas giant with no solid surface at all, or a moon locked in permanent, airless cold, or a planet close enough to its star that any delicate molecule would be destroyed by heat and radiation within moments of arrival. Earth, sitting at what turned out to be a remarkably fortunate distance from the sun, with liquid water pooling across most of its surface and just enough atmosphere to soften the worst of what space has to offer, represents only one of countless possible landing sites, and one of the few, as far as anyone currently knows, where a delivery like this had anywhere useful to go. Before this particular discovery, the picture connecting interstellar chemistry to meteorite chemistry had an obvious gap sitting right in the middle of it. Glycolaldehyde, with its 2 carbons, was confirmed in space. Ribose, with its 5 carbons and its direct role inside RNA, was confirmed in meteorites. Everything in between, the 3 carbon and 4 carbon sugars that would logically have to exist somewhere along that same ladder, remained unconfirmed in either setting, a missing middle section in an otherwise promising chain of evidence. Erythrulose does not close that gap completely. Glyceraldehyde and dihydroxyacetone, the 3 carbon rung, remain undetected in space to this day. But a 4 carbon sugar now sits confirmed on the interstellar end of that ladder, 1 rung closer to the 5 carbon sugar meteorites have already delivered, narrowing a gap that, until just this week, looked considerably wider than it does tonight. None of this diminishes what was confirmed inside that molecular cloud 26,700 light-years away. If anything, the delivery evidence gathered so far makes that confirmation matter more, not less, because it means the chemistry being observed out there is not chemistry happening in isolation, sealed away from anything relevant to a listener sitting in a warm room on a quiet planet. It is chemistry that has already, demonstrably, found at least some way to travel. Put the pieces of this chain next to one another, and something close to a complete picture starts to emerge, even if a few of its joints remain held together with hypothesis rather than certainty. A molecular cloud can build sugar-related chemistry on the icy surface of ordinary dust grains, patiently, over spans of time no laboratory could ever wait out, Exactly the kind of chemistry this discovery has now confirmed directly. That same chemistry carried inside the grains that eventually clump together into comets and asteroids appears capable of surviving the collapse of a cloud into a full solar system largely intact. Exactly the kind of chemistry meteorites like Murchison and comets like 67P have now confirmed directly as well. Somewhere in between those two confirmed endpoints sits our own solar system's early history, 4.5 billion years ago, when a young Earth, freshly cooled and still absorbing a steady rain of comets and asteroids left over from its own formation, may well have received deliveries of exactly this kind of chemistry. Two independent lines of physical evidence, one drawn from meteorites that have sat in museum drawers and desert sands for decades, the other gathered by a spacecraft that spent years matching its speed to a comet's, now point toward the same underlying conclusion from two completely different directions. That kind of convergence, separate methods and separate teams arriving at compatible answers without coordinating with one another, is exactly the sort of agreement that gives a hypothesis like this one real staying power in the scientific literature. It is worth remembering that the vast majority of comets and asteroids carrying this kind of chemistry never deliver it anywhere at all. Most continue orbiting for the entire multi-billion-year lifespan of the solar system without ever coming close enough to a planet to matter, drifting through the same quiet patterns they settled into billions of years ago. Only a small fraction ever cross paths with a planet's gravity closely enough to be pulled in, and of those, only a fraction of a fraction survive the fall, largely intact, rather than burning away completely in the atmosphere or vaporizing on impact. The chemistry has to survive not just its formation, and not just the collapse of the cloud into a solar system, but also a final, violent, mostly hostile roll of the dice before it ever actually reaches a planetary surface. There is something almost poignant about picturing it that way. A molecule assembled in patient darkness, folded into an icy grain, swept up into a growing comet, and sent drifting through the young solar system for millions of years before finally, perhaps, colliding with a barren, lifeless planet, still cooling from its own violent formation. It is not so different, in spirit, from a message sealed inside a bottle and set adrift on an ocean current, entrusted to a journey with no guaranteed destination, arriving intact on some distant shore only because the timing, the currents, and a great deal of patience all happened to align. None of this proves that erythrulose itself, this specific molecule from this specific cloud, ever reached the early Earth. That particular claim will likely never be provable, given how much time and how much geological churn separates us from those earliest days. What the evidence does support, cumulatively and with growing confidence, is something broader and, in its own way, more significant, that this entire category of chemistry, cold, patient, ice-grain chemistry, capable of building real sugars and real amino acids from simple starting materials, is not confined to one lucky cloud, one lucky laboratory measurement, or one lucky meteorite. It appears to be a standard feature of how molecular clouds work, the kind of chemistry that has likely repeated itself with only minor variations in an enormous number of similar clouds scattered throughout the galaxy, both long before our solar system formed and continuously ever since. If the ice-grain chemistry responsible for erythrulose really does operate as a general rule rather than a rare exception, then every one of the thousands of molecular clouds scattered through the Milky Way becomes a candidate location running some version of the same slow experiment, each on its own timeline, each with its own particular mixture of raw ingredients and available energy, each a separate roll of the same patient dice. Most of those clouds will never be searched this carefully. Most will never sit near two radio dishes willing to spend years listening to them. But the chemistry inside them does not require an audience to keep happening. This is, in fact, part of why questions like this one keep pulling astrochemists back to the same handful of promising clouds, searching for the next rung on the same ladder, hoping each new, confirmed molecule narrows the gap a little further between what a cloud is confirmed to contain and what a meteorite has already been confirmed to deliver. If that is true, if this kind of chemistry is closer to a common feature of galactic weather than a rare and precious accident, the conversation has to shift. The question stops being whether it could have happened here, on the early Earth, alongside everything else that eventually became life. The question becomes how often it has happened everywhere else, in how many other clouds, around how many other young stars, on how many other worlds that have never once heard of raspberries or kitchens, or the particular sugar that started this entire story. That question, how often, in how many other places, does not have an answer yet, and it may not have one for a very long time, if ever. But before going any further into what this discovery might mean, it is worth pausing to be precise about what it does not mean, because precision matters here more than almost anywhere else in this story. Erythrulose is not, itself, a piece of your DNA or your RNA. It does not appear anywhere in the genetic instructions carried inside a single cell in your body. The sugar that actually performs that role is called ribose, a slightly larger, 5-carbon relative, one rung higher on the same ladder this whole story has been climbing. Erythrulose is closer to an early draft than to the finished manuscript, a smaller, simpler cousin that shares the same basic family resemblance without doing the same essential job. Nor does this discovery prove that life began in space. No scientist involved in this research has claimed that, and the evidence does not support it. What has been confirmed is something narrower, and, once you sit with it, almost more interesting, that the chemistry needed to build a real sugar, the actual raw material biology eventually leans on, can assemble itself before there is a planet, a star, or anything alive anywhere nearby to make use of it. The ingredients can get a head start. What happens to those ingredients afterward, whether they ever find their way into anything resembling life, is a separate question entirely, one this discovery does not answer and was never designed to answer. It would have been easy, honestly, for a story like this one to get told differently, with far less care about that distinction. A less careful telling might have simply said, scientists found life's building blocks in space and left it there, technically true in the loosest possible sense, but stripped of everything that actually makes the finding worth understanding rather than just repeating. The difference between a real discovery and an exaggerated headline usually comes down to exactly this kind of precision, the willingness to say what something is not just as clearly as what it is, even when the honest version is quieter and harder to compress into a single dramatic sentence. There is an important difference between having ingredients and having a finished dish, one that is worth taking seriously rather than rushing past. A kitchen counter holding flour, sugar, eggs, and butter does not contain a cake. It contains the possibility of one, along with the possibility of 100 other things, or of nothing at all, if nobody ever walks into that kitchen and does the work of combining them in the right order, at the right temperature, for the right amount of time. Biology is considerably more demanding than baking. Turning a handful of confirmed prebiotic molecules into something that can grow, repair itself, and reproduce required an almost unimaginable amount of additional chemistry, organization, and time, most of which remains only partly understood, even for the one planet where scientists know for certain it actually happened. Sugar alone, even a true, complete, chirally correct sugar, was never going to be sufficient on its own, and it is worth being honest about everything this particular molecule still leaves unaddressed. Nobody has confirmed, anywhere in interstellar space, the kind of self-replicating chemistry that would eventually need to emerge for any of this to matter to biology directly. Nobody has confirmed the specific conditions under which loose molecules first organize themselves into anything resembling a cell. Those remain separate mysteries entirely, arguably far larger ones, and nothing about tonight's discovery pretends to have touched them. This is precisely why Jimenez Serra and her team are not stopping here. Confirming erythrulos was never the final goal of their work, only the most recent milestone in it. Their next target, already underway, is ribose itself, the actual sugar used inside RNA, the molecule that would represent a far more direct link between confirmed interstellar chemistry and the specific biochemistry every living thing on Earth depends on. If ribose is ever confirmed drifting through a molecular cloud the way erythrulos just was, the argument connecting cosmic chemistry to earthly biology would grow considerably harder to dismiss as coincidence. It is worth appreciating, for a moment, exactly what kind of patience a search like that requires. Years pass between one confirmed molecule and the next, most of them filled with failed candidates, false alarms, and long stretches where nothing new turns up at all. Nobody funds this kind of work expecting quick results. Nobody builds a career in this field chasing headlines, since most years produce none. What sustains it instead is something closer to quiet, stubborn faith, the conviction that a question worth asking is still worth asking even after the 10th or the 20th year without a clear answer. The same conviction that apparently led one research team back to the exact same unglamorous cloud year after year until it finally gave up a molecule worth the world's attention. There is something worth sitting with in the fact that this molecule carries a handedness at all, the same handedness biology itself depends on. It would have been entirely possible, as far as anyone understands the underlying physics, for a molecule like this one to form, with no preference whatsoever, an equal mixture of both mirror image versions, neither one more common than the other. Exactly the outcome most laboratory chemistry on Earth actually produces when nothing intervenes to tip the balance. That erythrulos exists as it does, carrying the specific shape it carries, does not by itself prove anything about how life's own preference for one hand over the other first arose. But it keeps that door open, a door many scientists once assumed had to be firmly shut, sealed by whatever happened here on Earth and nowhere else. It is worth noticing, too, how long a chain of human effort this single evening story actually rests on. A chemist in 1848, sorting crystals under a simple microscope, first noticed that molecules could carry handedness at all 178 years before tonight. A different team, 26 years ago, found the first sugar-related molecule drifting through this same general region of the galaxy. Another team, 7 years ago, pulled sugar directly out of a meteorite that had been sitting quietly in a museum drawer for decades. Most of them likely never imagined a 4-carbon sugar would eventually be confirmed drifting through interstellar space at all. Each one simply did the next careful piece of work in front of them, adding one more small, patient piece to a puzzle none of them could see the whole of, and left the rest for whoever came next to pick up. None of this should feel unsettling, though it would be understandable if, at first pass, it did. There is a familiar instinct When confronting discoveries like this one, to reach for a sense of smallness bordering on dread, the feeling that if the raw material for life is scattered so casually through the galaxy, then whatever makes a person suddenly seems less special, less chosen, less its own. That instinct, understandable as it is, gets the emotional arithmetic backward. Discovering that the universe is generous with its ingredients does not make any single result of that generosity less remarkable. It makes the whole enterprise feel less lonely. Somewhere in Spain tonight, the radio dishes that made this discovery possible are very likely still turned toward the sky, still listening, as they have for years, to the same unglamorous stretch of stars they have always been pointed toward. Jimenez Serra's search did not end with erythrulos, and it will not end with ribose either, whatever that particular search eventually reveals. There will be another cloud after this one, another candidate molecule, another long stretch of careful, patient, mostly invisible work standing between one confirmed discovery and the next. That is simply what this kind of science actually looks like, far more often than any single triumphant headline ever manages to convey. It is worth returning, directly and honestly, to the question this story opened with, because a title promising to explain why you exist deserves a straight answer rather than a dodge. Erythrulos did not make you. No single molecule did. You exist because of an almost incomprehensibly long chain of chemistry, geology, biology, and chance, stretching back through billions of years of evolution, through the specific conditions of an early Earth that happened to have liquid water and a stable enough sun, through whatever combination of ingredients first assembled into something capable of copying itself. Sugar was never going to be the whole answer, and no honest telling of this story should pretend otherwise. There is a reason stories like this one draw an audience at all. Late at night, when the practical business of the day has finished and there is finally room for a bigger question to surface. Human beings have always wanted to know where they came from, long before anyone had a telescope capable of listening to a molecular cloud, long before anyone understood what a molecule even was. Ancient peoples looked at the same night sky and told their own stories about origins, stories built from myth rather than measurement. But reaching for the exact same underlying question this evening has spent its time exploring. Tonight's version of that story happens to be built from radio telescopes and laboratory spectroscopy rather than myth, but the impulse behind it, the simple, stubborn human need to understand where any of this came from, is exactly as old as it has ever been. There is something worth pausing on in the simple fact that the signal confirming this discovery left its source long before anyone capable of receiving it, or understanding it, or caring about it had even evolved. For nearly the entire 26,700-year journey that light spent crossing the galaxy, nothing on Earth existed that could have made any sense of it at all. Humanity, in any recognizable form, only became capable of listening for a signal like this one within roughly the last century, an almost imperceptibly thin sliver at the very end of that entire journey. The sugar had already been assembling itself for a very long time before there was anyone here even capable of being curious about it. What erythrulos actually offers is something quieter and, in its own way, more durable than a single dramatic answer. It offers one confirmed piece of a much larger puzzle, evidence that at least one class of the chemistry required for something like you to eventually exist does not need a planet, a warm ocean, or a hospitable climate to get started. It can begin in the freezing dark, near the crowded, violent center of a galaxy, inside a cloud with no name most people will ever remember, built one patient collision at a time by nothing more deliberate than physics and time. That is not the whole story of why you exist. It is, at most, the very first sentence of a story that took billions of years and countless additional chapters to finish, most of which remain, honestly, still only partly written even now. There is a particular kind of knowledge that gets passed down quietly across generations, a grandmother's method for knowing exactly when a pot of preserves has thickened enough, a father's trick for coaxing a stubborn engine back to life. Small, inherited certainties nobody ever wrote down because writing them down never seemed necessary. Science works differently, deliberately so. Every measurement gets written down, every method gets published, scrutinized, and made available for a stranger on the other side of the world to repeat exactly. It is a less intimate kind of inheritance than a family recipe, but it is, in its own way, no less an act of care, one generation of researchers leaving behind exactly what the next generation will need, so that nothing important has to be rediscovered from nothing. There is something quietly moving, too, in the act of naming itself. Before this month, erythrulose existed, presumably exactly as it exists now, drifting through that same cloud for longer than anyone can precisely say. It did not need a name to exist. It did not need anyone's attention to keep assembling itself, one patient collision at a time. And yet, the moment a name finally attached itself to that molecule, published, confirmed, entered into the permanent record of what humanity understands about its own universe, something changed. Not out in the cloud itself, where nothing changed at all, but here, in the much smaller, much warmer space of human understanding. Naming a thing does not create it. It simply marks the moment someone finally noticed. The tools available for this kind of search keep improving year after year, and each improvement widens the range of what future discoveries like this one might reveal. Radio telescopes continue growing larger and more sensitive. Laboratory techniques for measuring the fingerprints of increasingly complicated, increasingly fragile molecules keep advancing as well, opening the door to studying substances that would have been impossible to work with even a decade ago. None of this guarantees ribose or any other specific molecule will turn up next. It only guarantees that the search itself will keep getting easier, keep covering more ground, keep listening more carefully to clouds like this one, scattered by the thousands throughout a galaxy that has, so far, shown no sign of running out of secrets to share with anyone patient enough to keep asking. If any part of tonight's story leaves you with a small, unfamiliar sensitive closeness to something that, only an hour ago, would have felt impossibly distant and abstract, that feeling is worth trusting. It is not sentimentality, and it is not an exaggeration built for effect. It is simply what happens when the actual scale of a thing finally becomes visible, when a molecule small enough to dissolve invisibly into a cup of tea turns out to share its exact shape with something drifting through the coldest reaches of the Milky Way. Distance, it turns out, is not always the same thing as separation. Knowing a fact and feeling its weight are two different things, and most of this story, up to this point, has lived mostly in the first category: careful measurements, confirmed frequencies, honest hedges about what remains uncertain. It is worth allowing the second category in as well, just for these last few minutes, before the night takes over entirely. There will likely be other names, other molecules, other careful announcements in the years ahead, each one adding its own small, honest piece to the same unfinished picture. Erythrulose will not be the last word on any of this. It was never trying to be. There is, perhaps, something fitting about hearing a story like this one at the end of a day rather than the start of one, in the stillness of a room settling towards sleep rather than the rush of one waking up. The chemistry this hour has traced took its own time, unhurried, across spans that make a single human lifetime look almost instantaneous by comparison. Nothing about it was rushed. Nothing about it needed to be. Space itself is famously silent, of course. No medium for sound to travel through, no air to carry a voice or a note across that emptiness. And yet this entire story has been built around the idea of listening anyway. Radio dishes tuned to catch whispers too faint for any other method to detect. Scientists patient enough to sit with silence for years at a time, waiting for it to finally say something. There is an odd, quiet symmetry in that. A story about listening carefully to the silence of space, arriving at the end of a day spent listening to very little at all, settling now into the particular silence of a room where someone is finally ready to close their eyes. Think back, one more time, to that raspberry warm from the vine, or to whatever version of that memory you happen to carry with you into tonight's story. Nothing about that memory has changed. The fruit is still just a fruit, sweet and ordinary and entirely unremarkable in the way that only genuinely good, simple things manage to be. What has changed, if anything has changed at all, is what sits underneath that ordinariness once you know to look for it. The specific sweetness on your tongue traces back to a molecule that also exists right now, tonight, drifting through a cloud of gas near the center of the galaxy, tens of thousands of light years from the nearest kitchen, assembled by nothing more than cold, dust, and patience, with no one there to taste it, and no one there to name it, until, eventually, someone finally did. That is the truth this entire story has been quietly building toward, and it is not a truth that needs any embellishment to feel significant. Ordinary is doing a great deal more work than the word usually gets credit for. The sweetness in a piece of fruit is not merely a pleasant accident of biology, confined to one small planet and its particular arrangement of soil, rain, and sunlight. It is also, apparently, a pattern the universe is capable of writing out on its own, in the coldest and least hospitable places it has to offer, long before there is any fruit, any soil, or any planet for that pattern to eventually land on. There is a difference, too, worth naming plainly, between what scientists mean when they say confirmed and what that word sometimes gets stretched to imply in casual conversation. Confirmed, in this context, means exactly and only this: erythrulose exists in that specific cloud, detected through 12 independent spectral lines, verified against a laboratory measurement, and published after passing through the scrutiny of other scientists who had every incentive to find a flaw if one existed. It does not mean solved. It does not mean finished. It means one narrow, specific claim has cleared an extremely high bar and stands now as solid ground for whatever comes next to be built on. Tomorrow morning, or whenever this particular night finally gives way to something else, very little about the ordinary world will look any different on the surface. Fruit will still just be fruit. Sugar will still dissolve quietly into coffee or tea, without announcing anything about its cosmic relatives. The universe has no interest in making its connections obvious, and it rarely bothers to explain itself in ways convenient for the people trying to understand it. That has always been part of the work, and part of the appeal, of paying close enough attention to notice anyway. Future papers on this same general topic will very likely cite this particular finding for years to come, one more data point in an argument that keeps slowly accumulating weight with each new piece of evidence. That is how science actually accumulates meaning over time, not through single decisive moments that settle everything at once, but through exactly this kind of steady, patient layering, one confirmed result resting on top of the last, available for whoever comes next to build upon, or, if the evidence eventually demands it, to revise. It is easy, especially late at night, to want a story to resolve itself completely, to end on a single clean answer, rather than a widening set of careful, honest questions. This story will not do that, and pretending otherwise would betray everything it has tried to be faithful to along the way. Perhaps you remember exactly where you were the first time you heard that human beings had walked on the surface of the moon, a piece of news that once felt like the outer edge of what anyone could reasonably expect science to accomplish in a single lifetime. Discoveries like tonight's rarely arrive with that same singular, unmistakable drama. They arrive quietly instead, one careful paper at a time, one confirmed molecule at a time, easy to miss entirely unless someone happens to be telling you about it at exactly the right moment. That quietness does not make this discovery smaller. It only makes it easier to overlook. There is no tidy bow to place on a story like this one, and it would be dishonest to pretend otherwise. The cloud is still out there, 26,700 light-years away, doing exactly what it was doing before anyone on Earth ever pointed a telescope its way, indifferent to whether anyone is listening. The search for ribose is still underway, its outcome still unknown. The question of how, or whether, any of this chemistry actually reached the early Earth remains, and will likely always remain, a matter of careful inference rather than certainty. What is settled, what this discovery has quietly and permanently added to what humanity knows about its own origins, is smaller than a headline promising to explain your existence might suggest, and larger, in its own way, than most headlines ever manage to be. Somewhere in the cold and the dark, long before there was anyone to taste it, something sweet was already being written into the universe's own patient, ongoing recipe. Tonight, for the first time, someone finally read a little further into that recipe than anyone had managed to read before. Rest now. Somewhere in the cold and the dark, something sweet is still taking shape.